Hello class, welcome to this video on AP Stats Chapter 3 review. So we're going to go ahead and get started. The progression should be in the same kind of order as the book, for the most part, 3-1, 3-2, 3-3. So the first question is you got a scatter plot and you want to describe the relationship here between the final grades and the number of days absent. So it's just describing the direction. You can see that it's linear and it's going down. So it's a negative relationship. So all you got to say is that it's a negative relationship. So we're going to say, to describe it, we're saying there is a negative relationship. All right, so there is a negative relationship between the number of days absent and the final grade. All right, and that's pretty much it. So you have to describe that relationship. Nothing crazy. So, as the number of days increases, the final grade decreases. So there's that negative relationship. All right, so number 2 says a random sample of students from Tar Heel Academy. So kindergarten to 12th grade private school in North Carolina was selected. So we got information on age and height. It says identify the explanatory variable and the response variable. Okay, so remember that the explanatory variable helps explain the change in the response variable. And so we would say that the explanatory variable would be the age, since the age helps explain what the height is going to be. Like the older you are, then generally the taller you get, right? So that's generally the relationship. So we would say that age on the explanatory variable is the age in years, and response variable is height in centimeters. Okay, and then part B, it says if the data were to be displayed in a scatter plot, what scale would be appropriate for the horizontal axis? So if you look at the age, it looks like the ages are from 5 to 18. And we have 6, 8, we have 10, 12. So you could potentially go by twos, right? So maybe starting at 4 and then going all the way to 18 and then go by twos. So you could go from 4 to 18 counting by twos. Okay, so that would be an appropriate scale for the x-axis. Now, what scale would be appropriate for the y-axis? So here we got the lowest is around 114, and the highest is around 181. So, and it looks like you got 120, 130, almost 140. So you could go by tens, maybe starting at 110-ish and then going, or 100. So maybe 110 would be closer to maybe around 190. Okay, so you could go from 110 to 190 counting by tens. All right, so there's that. So next one, number 3, according to the recent article from a business magazine, employees who stay in companies longer than 2 years can expect an annual salary increase based on the number of years loyalty to that company. Okay, so we got a number of years versus current annual salary. So we want to create a scatter plot. All right, so we're going to go ahead and make a scatter plot here. We're just going to make a small scatter plot. So number of years of employment looks like the smallest is 4, the largest is 18. So we could potentially go by twos from 4 to 18 for the x-axis. So we'll go ahead and do that. And then for the y-axis, our smallest is 85. So let me just highlight the smallest and the largest here. And the largest is around 125. So we could go from 85 to 125. We can go by probably by fives or something like that, or tens or whatever, maybe fives. and then we for the x-axis we can go by 2s. So let's go ahead and try that. I'll do it over here, just so I have a little bit more room. So here, this is going to be current annual salary. Thousands. And we have number of years of employment. Okay, so we're going to go by starting at 4 and go by 2s here. Okay, so we got 85, 90, 95, 100, so on and so forth. It's about 125. Okay, so then we can start graphing. So we got 10 and then around 97.3. So 10 and then 97.3, halfway. We got 6 and then 88.7. Just close to 89. We got 9 and 94.2. Close to 95. We got 15, 121. Around there. All right. 4 and then 85.3. 10 and 100. $18 and 125. And then 11 and 100.8. Okay, so we got a graph that looks kind of like this. And so then we can get a good idea of the graph. So there's my scatter plot. Describe the relationship between the number of years of employment and the current annual salary. So we can see that there seems to be a positive relationship here, and it seems to be linear. It seems to be strong. It seems to be very tight to the curve, to the line, that is. So I would say, remember, when we're doing this, we're describing a relationship, we need strength, direction, form, and then unusual outliers. There's no unusual behavior here. Okay, so there is a strong positive linear relationship between years of employment and current annual salary. And then we could say there doesn't appear to be any unusual behavior. Outliers or anything like that. All right, so next one, number 4, NCAA Division I men's basketball tournament, March Madness has been played. Okay, so this is based on the scatter plot. Describe the relationship between the number of teams left in the tournament and the round number. So you can clearly see here there is a curved relationship there, and it seems to be a strong, non-linear, negative relationship, right? And there doesn't appear to be anything unusual. All right, so we can say there is a strong negative non-linear relationship between number of rounds and number of teams left. In March Madness B-ball tournament, right? Basketball tournament. And like before, there is nothing unusual in the graph. Okay, so something like that. And then number 5, find the relationship for the relationship in the shown in the scatter plot. Which value is closest to, and then we just picked our answer. Okay, so we know it has to be negative because it's like that, right? So it has to be negative, so it has to be -1 or -1.5. But we know it can't be -1 because -1 is a perfect line. So the answer has to be -0.5. Moderate negative relationship. Okay, so number 6, an admissions officer, Columbia, believes the SAT math score for incoming students can be predicted using their reading and writing score. Okay, so it looks like we got something that appears to have that linear relationship. Which variable is the explanatory variable and which is the response variable? So from what they're saying, it says they believe that the math SAT score can be predicted using the reading and the writing score. So therefore, they're using, in this example, they're using the reading and writing score as the explanatory variable, okay? All right, and then it says correlation is 0.956, interpret this value. So remember, correlation is based on our linear relationship. So they're talking about the linear relationship here has a strength of 0.956. And so the linear is saying that it's very strong. 0.956 is very strong and it's positive, okay? So we would say that the linear relationship between reading and writing score and the math score is very strong and positive. All right, and then does the strong correlation mean that a change in the explanatory variable causes a change in the response variable? So they're talking about causes. Remember, correlation does not imply causation, so no. Since correlation doesn't imply causation. Even if we have a strong correlation. Okay. All right, so the next one, number 7, random sample 15 high school students generated from census at school includes the following data. Using technology, calculate the correlation of the relationship when foot length is the explanatory variable. All right, so I'm going to go ahead and show you this on using the TI-84. Remember that if you don't have access to a TI-84 and you don't have the software right now, you can use the app called Calculate 84, Calc 84, something like that, and you can download that on your Android or your iPhone, and you can have the same kind of setup here, or it's not gonna look exactly like this, but you're gonna have the same key layout and everything. So it's gonna be very similar. So I highly suggest doing that. But in any case, let's go ahead. What we're gonna do is we're gonna go to Stat and then Edit, and then we're gonna enter the data, which I've already done here to save time. So I got my list 1, list 2 for my foot length and arm span. Next, we're going to go to stat. So a couple things. If you go to vars and you go to statistics, that will give you your R value, which is what we want. However, if you go straight to your R value, when you go to equation, you got to go to equation. You go straight to your R value, it's not going to work. It's going to give you like undefined. Hold on, let me get out of this thing. You go to vars, let me go back to that. You go to number 5, statistics, go to equation, and you go to R. It's going to say undefined. And the reason why is because you have to do the regression line before you find R, okay? So let me go back to that. So I just wanted to let you know that that's something that you have to be aware of. So first you're going to go to stat and calculate. We're going to do the regression line first before finding the correlation, because they want correlation, right, which is R. But first you're going to need to calculate your regression line. So linear regression, list 1, list 2. We're going to calculate. So now we got that. By the way, also, while I'm here, I might as well show you how to do the scatter plot. Remind you, if you want to do the scatter plot, you hit second, y equals, in order to do your stat plot. Enter, make sure that's turned on. And then when you go to zoom 9, and that's how you can graph it. So that's how it looks like. Now we just want to find the R. So I just want to show you how to do a scatter plot, because I might as well while I'm showing you. All right, so now let's go to vars and go to option 5. Option 5. Go to equation, and then we're going to go down to R. And that should give us our R value. All right, so we got an R value is 0.6926, around there. So I can go ahead and put that here. So R, about 0.693. Now we want to interpret the correlation R. All right, so remember the 0.69 is moderately strong. I kind of gave you an idea of what moderate is, right? Moderate is around 0.5, 0.6, 0.7, so on. Once you get to like a certain point, 0.8, 0.7, 0.7, 0.8, you know, starting to get strong. But here, 0.5, 0.6, up to 0.7-ish, I would say it was moderate, okay? So here, definitely we'll say moderately strong, and it's positive. Okay, so we're going to say the linear relationship between, in this case, foot length and arm span is moderately strong and positive. Okay, and that's it. Part C, calculate the correlation again, this time using arm span as the explanatory variable. So we'll show you how to do that. So basically we're swapping list 1 and list 2. So list 2 is now X and list 1 is now Y. Okay, so this is easy to do on the calculator. So first we're going to go to, let me get out of this. We're going to go to stat right here and then edit. And notice that we got our list 1, list 2. So we're going to say, we're going to use list 2 for X and list 1 for Y. Okay, so I'm not going to change anything here. All right, so let me go back. So I'm going to go to stat, I'm going to go to calculate, I'm going to go to linear regression. This time I'm going to swap list 1, list 2 here. So how do I do that? You have to hit second stat in order to hit list 2. Okay. And then Y list is going to be list 1. Second stat, list 1. There you go. That's it. I'm going to recalculate the regression line, and I get this time. But now when I try to calculate the R equals by doing vars and then number 5 for statistics, equation, go down to R. Notice the R is the same. It's the same R. And we shouldn't be surprised by that based on our notes, because if you swap X and Y, it's not going to change anything. Okay, so here the R is still the same. Oops, go back. All right, so R is approximately 0.693. Explain the impact of switching. And will this always be true? And yes, the correlation did not change, as it never changes when you switch the two variables. All right, so there you go. All right, so now we're looking at the next one, number 8. Fitness tracker records the number of steps the user takes each day and the number of calories burned. Okay, so we got number of calories versus number of steps. The user wishes to convert the number of steps taken each day to a distance. All right, so it says the user wishes to convert the number of steps taken each day to a distance. They determine that their average step is 2.2 feet long. Lowest number of steps is 1480. So all you got to do is just, it says to, you're just going to multiply those two in order to get the number of steps, right? Because this is, if their steps is 1480 and then their average step is 2.2, then you just multiply them. So 1,480 steps times 2.2 feet per step. Then you would get, to multiply those, 3,256 feet. All right, so that's how much, okay. So then part B, it says, will changing the explanatory variable from number of steps to distance in feet change the correlation R? And the answer is no, it's not going to change it, because remember that the correlation stays the same when you change the units. Doesn't change when you change units. Okay, so remember the formula for R is the sum of zx, zy divided by n minus 1. And so in order to calculate the R, we would need the z-scores, but the z-score is unitless. There's no units for the z-score. So therefore, it doesn't matter what the units are for x and y, whether you convert them or not, it's still going to be unitless. Okay. So part C, will changing the explanatory variable from number of steps to distance in feet change the units of correlation? So no, since the correlation doesn't have any units. Correlation doesn't have any units. Okay. All right, so number 9, the scatter plot shows the total number of flight passengers in 10,000s and the total number of flights in 10,000s each month in a recent year. Okay, so the correlation is 0.914. Describe the relationship in context. Okay, well, so they give you the R 0.914, so that's pretty strong, right? So we're going to say that there's a strong, and it seems positive, right? And it seems linear. Okay, so all right, so let's go ahead and do that. So there is a strong positive linear relationship between number of passengers and number of flights. Now here, if you look at the graph, there does appear to be an unusual feature. So if I were to graph this, let me see if I can graph this a little better. Most of the points are here. So what I can do is I can just do a graph kind of like that. Okay. And so we could see that there's a couple of unusual points, but pretty strong overall. So we could say at least maybe those two. Potentially, there are unusual points at, and then we could just put those values in. There are two unusual points at 5,500, and the y value is around 59, and so now this is 5,500. This is like going by 500s right here. So we'll say this one right here is maybe around 4,600, around there, and 63, right? Okay, so there's two potentially unusual points. All right. Now we're going to calculate and interpret r squared. Okay, so we're going to calculate r squared. Now they give us 0.914 for the r, so all we got to do is just square that. And they also want us to interpret it, so we also needed. So I'm going to leave some room to do that. Okay, so 0.914. You would get roughly 0.835. So we're going to convert that to a percent. So if we convert that to 8%, that's going to be 83.5%. Okay, so 83.5% of the variation in the y. What's the y? The y is the number of flights. Okay, and the number of flights. So 83.5% variation in the number of flights can be explained by the least squares regression line. With x equals the number of passengers. Okay. All right, so number 10, the monthly cost of electricity for a random sample of 40 homes during the summer month was recorded. Okay, so it says there was a strong negative linear relationship between monthly cost and the average temperature of the thermostat. The coefficient of determination is 0.862. What is the value r? Okay, so they say r squared is 0.862, and so to get r, we need to take the square root. How do we know whether it's positive or negative? Well, they just said it's negative here, so we're going to have to put a negative sign, okay? All right, and that's it. So you just take the negative square root of that. So square root of 0.862, so about 0.928, but negative. Okay. All right, that's it. All right, number 11, a random sample of 45 books is selected from the library. The number of pages and the weight of each book is recorded. The relationship between number of pages, okay, is multiplied by the equation. So we got an equation, that's important. What is the predicted weight for a book with 425 pages? All right, so we got our y-hat equation. So remember, x is the number of pages is x, right? And they say 425 pages, so that's x. So we're just going to plug this into y-hat. Plug it into the y-hat equation for x. Okay, so 2 plus that, and if you do that, you get 16.875 ounces. So 16.875 ounces. Right, that's the predicted weight. Now identify and interpret the slope. So the slope, remember, the equation is y-hat equals a plus bx. The slope is that, right? That's the slope, which is b. Let me just call that slope. All right, so the slope is equal to 0.035. Now, slope is rise over run, so it's y over x. The units of y are ounces, and this slope is positive. There's always an invisible 1 down here. The units of x are pages, right? So for every page. So this is saying for every page added to the book, so for every 1 page increase in the page, so for every 1 additional page, the weight, the predicted weight, increases by 0.035 ounces. Okay, so that's how we're going to kind of word it, or something similar to that. Okay, so for each additional page, the predicted weight of the book increases by 0.035 ounces. Okay. All right, identify, interpret the y-intercept. So the y-intercept, that's the y-intercept right there, is that 2. Okay, so the y-intercept is equal to 2 ounces. So what it's saying, it says, remember the y-intercept is when x is 0, when x is 0. So when x is 0, that means if you have 0 pages, the book is going to weigh 2 ounces. Okay, so a book with 0 pages, in other words, just the binding, right? You have the binding and then you have the pages. So it's just the binding, is predicted to weigh about 2 ounces. All right, that's it for that one. Number 12, at the end of semester, math teacher wonders if the student's attendance has an impact on the scores. So here's your scatter plot. What is the approximate y-intercept of the regression line? Okay, so the y-intercept looks like right there, so it looks like 90. So y-intercept is approximately 90. Interpret this value. So that means that if the student has 0 absences, then their final exam score is approximately a 90, right? That's basically what it's saying. A student with 0 absences is predicted percent on final exam. Okay. All right, part B, the slope of the regression line shown is negative 2.75. Interpret this value. So negative 2.75 over 1. Remember it's a rise over run. So the rise is the score, percent, right? The unit for A is absences. So for every one increase in the absence, right? For every additional absence, the score, the predicted final exam score, is going to decrease by 2.75%. Okay. So for each additional absence, the final exam score is predicted to decrease by 2.75 points. All right, use the regression line to predict the final exam score for a student with 4 absences. Okay, so here's 4 absences. We're going to look that up here. So that looks to be around the 79%, I would say, probably 79%, right? Okay, so it's approximately 79%. All right, part D, it says the student with 5 absences scored an 80 on the final exam. Did the student score better or worse than the score that would be predicted by the regression line? Okay, well, a couple ways you could do that. You can look at the 5 absences they scored an 80. Well, that's above the regression line. So that means that the student scored better than what was predicted, right? Because, we predicted it to be lower, but he predicted it to be higher. Okay. The point 580 is above the regression line, so the student did better than what was predicted. All right, so there you go. So number 13, the scatter plot shows the vehicle weight in pounds and the highway fuel economy miles per gallon for 15 different trucks. And they give you computer output. Okay, so using the computer output, remember this is a constant, so this is your A, this is your B, right? Okay, so write the equation of the regression line. Be sure to define any variables. We want to make sure to define stuff. Okay, so we're going to say y hat equals A plus bx. So 42.167 plus, or I'm just going to say minus 0.004x. Okay, so there's your regression line, and then we got to define what y hat is. So y hat is predicted highway fuel economy, and x is the weight in pounds. Okay, that's it. So part B, what is the value of the correlation of the relationship? Okay, so we want to find the value of the correlation. Well, we know the R squared is 0.427. We know the relationship is negative as well. So we know that the R is going to be negative. Okay, so we're going to do R equals negative square root 0.427. Remember R squared was 42.7% according to what they said. Yeah. So convert that to a decimal, which is 0.427. Take the square root of that, and we get about negative 0.653. All right, now it says the GMC Sierra weighs 4,400 pounds. Predict the highway fuel economy for the GMC Sierra using the regression line. Okay, so we got the regression line. We're gonna, it says 4,400 pounds. We're gonna put that in for X. Okay. Plug that into there, we get 24.567 mpgs, miles per gallon. That's the predicted highway fuel economy. GMC Sierra has an actual highway fuel economy of 29 mpg. What's the residual? Okay, so residual equals y minus y hat. This is the y, and we just calculated the y hat, 24.567, right? So that's 4.433 miles per gallon. All right, and that's it for that one. Number 14, the relationship between height and weight for a random sample of polar bears is modeled by the equation. Okay, so we got our equation here. Let me double check here. So the weight, it should look like that. So I don't know why that's doing there. Okay. The largest polar bear on record was, so it's the weight hat equals that. So this is like your y hat, right? And then this is like your x, your height. So basically, if we were to rewrite it, it would look like y hat equals 475x minus 3250. So they're tricking you because they put the x term here first. So they put the bx plus a afterwards. The largest polar bear on record was found in Alaska in 1960. He was 12 feet tall and weighed 2,210 pounds. Calculate and interpret the residual for this polar bear. All right, so first we're going to need to calculate the y hat. So the weight hat is 475 times 12 feet tall minus 3,250. Okay. So I got 2450, so 2,450 pounds. And then we're gonna, it says it was actually 2210, so that's the y. Okay, so residual equals y minus y hat, 2,210 minus 2,450. So that's negative 240 pounds. All right, we want to interpret. Okay, so that means that the actual weight of the polar bear was 240 pounds lighter or less than the prediction, right? Less than the weight predicted by the regression line. For height of 12 feet. All right. So number 15, a country's natural resources. Okay, so oil, gas, and coal can greatly impact the overall economy, which is the GDP. All right, so using technology, find the least squares regression line relating the revenue from natural resources and the GDP. Be sure to define any variables used. Okay, so the natural resources influences the GDP. So that's X and then that's Y. All right, so this is going to be list 1, list 2. We're going to plug this into the calculator. All right, so here we go. So we put in the data into the X into the Y. We got the natural resources here, the GDP here. And so now that we typed that in, we did it using stat edit. Then we're going to go stat, we're going to go to calc, and then go to linear regression. List 1, list 2, you can calculate. All right, so then remember, they have it as ax plus b. So remember, it's going to be b plus ax. So it's going to be this part, a and b are swapped. But we got this plus this x, okay? So negative 2.967x, or negative 2.967 plus 2.9279x, okay? So that's how it's going to look like. All right, so let's go ahead and do that. So we got y hat equals negative 2.97, we're just going to use 2 decimals, plus 2.93x. Where y hat equals predicted GDP and x equals natural resources. In billions. And then, of course, GDP is also in billions. All right. And then using the least squares regression line to predict the GDP for a country with a revenue of $50 billion. Okay, so we got y hat. So that means x equals 50. Okay, $50 billion. To do that, all right, so we get 143.53. All right, so that's going to be 142.53 billion dollars. All right, and that's it for that one. Number 16, the amount of sugar in grams and the number of calories in a 12-ounce serving of 10 different popular soft drinks are shown in a scatter plot, and we got a residual plot next to that. It says the sum of the squared residuals is 2,219.9. Which point contributes the most to the sum? Well, the point that's going to contribute the most to the sum is the one that's farthest away from the line, which is that one, right? So that one is about 54 and 210, right? So the point 54 would contribute the most. since it has the largest vertical distance. From the regression line. All right, is a linear model appropriate for this data? Well, you can see that there's kind of a curved pattern here, right? You can see a curved pattern. So I would say no, right? It's not. So no. There is a curved pattern in the residual plot. All right, so let's look at the next one. All right, so it says the scatter plot shows mean annual precipitation in centimeters and the mean annual temperature in degrees Celsius for 21 different forest regions. Describe the relationship between mean annual precipitation and mean annual temperature. Okay, so we can see it. There's a linear relationship. If you look at the, can we look at the R? Okay, so they don't give you the R here in the computer output. But you can see based off of this, it appears to be, it's not strong. I would say moderate, maybe like 0.4, 0.5 or something like that. If not, so I would say on the low moderate side, but I would say moderate here based off of this data. So describe the relationships. I would say a moderate, positive, a linear, based on what we see here. And there might be an outlier. If you look over here, that looks to be an outlier around 250. If you look at the data, it's a little bit hard to tell from here, but I would say maybe potentially an outlier there, potentially. Okay, so there's a moderate, positive, notice that this has the greatest vertical distance away. This one isn't as large, but as that one, the one that I picked out. So there's a moderate positive linear relationship between mean annual precipitation and mean annual temperature. There appears to be an outlier. At around 250.15. Okay, so write an equation for the least squares regression line. So this is my A, this is my B, so that's not bad at all. So y hat equals 10.303 plus 0.053x, where y hat is predicted mean annual temp, x is mean annual precipitation. All right, part C, wet tropical forests are designated as areas with 140 to 220 centimeters of precipitation per year. Create an interval for the predicted mean annual temperature. So basically this is like your x, and that's also an x. So basically you're plugging in x twice to get two different y hat values. Okay, so we'll plug in the 140 first. All right, so if I plug that in, I get about 17.723 degrees Celsius and then 21.96 degrees Celsius. So my interval is from this to that. Okay. All right, so number 8, at the end of a semester, a math teacher wonders if student attendance has an impact. Okay, so we've seen this before, but this time they give you a residual plot, and they're asking, is the linear model appropriate? Yeah, this does appears to be random, right? You can see it does appear to have an element of randomness. Okay, so I would say yes. There is a random scatter on the residual plot. All right, what is the actual exam score for the student with 5 absences? Round to the nearest whole point. All right, so here the actual exam score, that's your y. For student with 5 absences, so x equals 5. So if I look at the residual plot, that's for 5 absences, it appears that there's a residual of 4. Okay, so we know that the residual is 4. So let me do that here. So residual equals y minus y hat. And we know that the residual is 4, right? So let me put here residual is approximately 4. So we get 4 is equal to y minus y hat. Now, how do we get y hat? Well, we know what the equation of the regression line is. So let me just do that here. Right, based on this A and B. So we can plug in 5 into that. And if we do that, 89.943 minus 2.755 times 5, so we get about 76-ish, so approximately 76. So we get y minus 76 equals 4, and then if we solve both by adding 76 to both sides, then we would get an actual of 80. Okay, so about 8. So that's how you do it. So we got the residual from the residual plot. We got the y hat from the calculated output, and that gives us the actual. Okay. All right, so there's your work there. All right, so next one, number 19, Emily works as a customer service representative answering customer emails. For 8 days, she records the amount of time she spends answering emails. So here's a list of residual. The mean of the residuals is 0, and the standard deviation of residuals is 4.07. So that's your S. Okay, so they're giving you your S here. Interpret the S. Okay, so this is just interpreting standard deviation of residuals. Okay, so remember, standard deviation of residuals is the typical variation of the typical residual. Okay, so how much did the residuals typically vary by? Okay. So if we want to interpret that, we say the residuals typically vary by 4.017. 4.017 what? 4.017 emails. Okay, so let's talk about emails here. They vary from what? From the mean, right? From the mean of 0. All right, so there's that. Another way you could do this or interpret it is like we did in the notes is because remember it says the amount of time she spends answering emails, right? This is the amount of time and then emails. So what we could say, we could also say, or we could say the actual number of emails answered typically varies, or is typically about, or rather I would say is typically about 4.017 away from the number predicted by the least squares regression line. with x equals, what was x is the time, right? Yeah, amount of time spent. Okay, so a couple of different ways that you could do this. If you know, either one would be fine. All right, so number 20, consider the following scatter plot. Classify each of the two marked points A and B with any of the following descriptors that apply. Okay, so we just have to describe the graph basically. Okay, so we'll go ahead and do that. Okay, so if you look at the where most of the data lies, the average of this data is around here in the x direction, x bar, and the average in the y direction is around there, y bar. So I would say A is definitely a vertical outlier because look, if the most of the data is here, which is where these are going to cross, right? X bar and y bar. Oops, I already labeled y bar, so let me get rid of that. Then, yeah, so in that case, A is a vertical outlier because it's definitely far away from in the vertical direction. Okay, so I would say A is a vertical outlier. I would also say that A is an influential point because if it's a vertical outlier, it's going to change. What it's going to do is it's going to pull the line up. And so that's going to change the y-intercept. Okay, so that means if it changes something significantly, it's going to be an influential point. All right, and B is definitely a horizontal outlier. Now, notice that B is also going to be high leverage because a high leverage point is a point that is a horizontal outlier. So a point that has that is very far away from the data in the x direction, or very it's a distance, significant distance away in the x directions. So I would call it high leverage, and it's influential. Okay, so that's what that is. All right, and then number 21, the scatter plot shows the weights in pounds and the gas mileage in miles per gallon for 9 different vehicles. A least squares regression line is also shown. Okay, so estimate the coordinates of x bar, y bar, where x is the weight of the vehicle in pounds and y is the gas mileage in miles per gallon. Mark the point on the scatter plot. Okay, so they want you to kind of estimate it. So if I were to estimate it, it'd probably be right here might be x bar, and then right around here will be y bar. And the x bar, y bar has to be on the regression line. It can't not be on the regression line where they cross, okay? So the x bar, y bar has to be on the regression line. So that means it looks like it's about 4,026, okay? So approximately 4,026 would be the my point. If the point 4,021 is added, how would the y-intercept be impacted? So if I added 4,021, so like if I added it here, well then what it's going to do is that it's going to pull the line down. So if you have a vertical outlier, it's going to pull the line, is going to have a pulling behavior. So in this case, it's going to pull the line down. If it's a horizontal outlier, it's going to tend to pivot, right? Pivot the line. But here it's going to pull it down. So it's going to decrease the y-intercept because now it's going to change pull it down. But the slope is not going to change. It's just going to be the y-intercept, okay? So the y-intercept would decrease. Now the slope would remain unchanged though, right? So slope approximately the same. Okay, now just to give you another example, if I have a point like that's over here in green, let's just say here, well then that's far away from the x, right? The x bar. And so what that's going to do is it's going to pivot the line. So it's going to go like that and then like that. And so that means the slope is going to be smaller or less negative. And and then the y-intercept is going to decrease as this goes down, right? So that's how you kind of interpret behavior, okay? So hopefully that makes sense. Okay. All right, so number 22, it says consider falling skypath. What effect does the point 8586 have on the correlation between x and y? So 85 is here, and then this is, so they're talking about this. So now, because notice that that point is in the same trend as the line, so that means that it's actually strengthening the correlation. Okay, it's making it really strong. So the point 8586 is in the pattern, so it makes the correlation stronger. Okay. All right, so the next one, 23. Daytona 500 NASCAR race is a 500-mile race. Okay. It says, not surprisingly, the driver's average speed is correlated to the length of time it takes to complete the race. Okay, so the length of time is x, and the speed. No, I got it reversed. It's not the length of time. It says the faster you are, the average speed. The faster you are, then the less time you're gonna need, right? Is the length you're gonna have less time to complete the race. Okay, so the faster you are. So x is the average speed. It helps explain the time to complete the race. Okay, so the average speed. All right, so they give you that. Okay, so they give you your R, the mean and standard deviation are, okay, so they actually give you all this information. So it's pretty straightforward if you know the formula. Okay, so we know that y hat is equal to a plus bx, and the formula for b is r times sy over sx. All we got to do is plug in the numbers. We got the numbers. We got our r. Then we got to plug in our sy over sx. Calculate that. So we get negative 0.924. And now we're going to get a. So a is equal to y bar minus b x bar. Now y bar is 197.3 minus, now we're going to plug this in there, times x bar. We get 336.362. So then we can plug it into that. So y hat equals 336.362 minus 0.924x. That's it. Plug it into a plus bx. That's all there is to it. All right, number 24. Consider the following data for players at the linebacker position at the recent NFL Combine. Okay. Calculate x bar and y bar. Okay, so x bar is just when you average this is x, this is y. So you're going to average the values in the x direction. So to x bar, you're just going to add these up, divide by how many you have. 2, 4, 6, 8. There's 9 players, okay, in here. So you got to add these up. Plus dot dot dot. Then divide by 9. So you get 4.508 approximately. And then the y bar, you're going to just do the same thing. So 29 plus 25 plus dot 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 all the way to 14. Just add up all these numbers. Divide by 9. So that's approximately 21.333. So there you go. So that's your x bar, y bar. Now, using x bar and y bar from part A, explain why this equation can or cannot be the equation of the least squares regression line. Okay, so what we had to see is, okay, if I plug in x bar into this equation, for x, will I get y bar? If I don't get y bar, then this cannot be the least squares regression line, okay? Because the least squares regression line has to have x bar, y bar as part of the line. Okay, so let's see if that's true. So we get 310.523 minus 57.394 times, now I'm going to plug in x bar, 4.508. And let's see what I get. 310.523. So 51.79, okay. But notice that does not equal to 21.333. That's the y bar, right? So it doesn't equal. Therefore, this cannot be the equation. So no. This cannot be the equation of least squares. Because x bar, y bar is not on the line. Okay, so that's how you do it. All right, so the next one, 25. The population of Austin, Texas has been growing exponentially since 1950. Scatterplot grows graphs the years since 1950 versus the log. Okay, so we're looking at another lesson here. This is going now to chapter 3, lesson 3. Okay. All right, so so we're graphing the log versus the years. And it says the equation of least squares regression line is given by this, where x is years. Okay, right. So interpret the meaning of 5.0941 in the least squares regression line equation. Okay, so this is the equation, I guess, right here. Okay, so the 5.0941, that's the y-intercept, right? And the y-intercept is when x is 0. And so what it's saying is that when x is 0, that means when the year is 1950. Okay, so in 1950, I guess we could say in 1950, the predicted what? Well, here we're talking about the log of the population. So we're saying that the predicted log of the population is 5.0941. Okay, so that's what that is. And then for part B, it says interpret the meaning of 0.0172. So that's this number right here. So that's a slope, right? So let me write that out. So 0.0172 over an invisible 1. So now remember that the units of y is log, right? So this is actually log of y. And this right here is per year, right? So what it's saying is that, and it's positive. So that means that it's going to increase. Okay, so that means that the log of Austin's population is predicted to increase by 0.0172 for each year. Okay. All right, and then part C, use the least squares regression line to predict the population of Austin, Texas for the year 2010. All right, so so x is equal to, we got to do 2010 minus 1950. So that's 60, because remember, x is the number of years since 1950. So that's going to be 60 years. All right, so then we have that the log of y hat is equal to, remember it's a log because that's what it says here, the log of the population, is 5.0941 plus 0.0172 times x, right? And x is 60. Actually, let me just write 60 and then I'll plug in the x there. Okay, so that's the model, and then we're going to plug in x. So we get log of y hat is equal to, so let's plug that in and see what we get. Okay, so 6.1141. Okay. Now we're going to solve for y. So how do we solve for y? Well, we solve for y by, remember, the base of log is 10. So we're going to do 10 raised to the log power, 10 raised to that power. And the 10 and the log cancels. Okay, that's the beauty of it. These cancel. So we get y hat is equal to 10 to the 6.1141 power. All right, let's see what that is. So it's 1,300,000. Okay. So this is a scientific notation. So this is 300,000. Yeah, 1,300,500 people, approximately. Okay, so about 1.3 million people. All right, so there's that one. Okay, so 26, the scatter plot shows a number of annual scholarly publications on the topic of artificial intelligence. X is the number of years since 2010, Y is the number of publications. Describe the relationship between the two. Okay. All right, so it does appear to be curved and doesn't appear to be linear, okay? So there is a strong positive non-linear, in fact, exponential relationship between years and the number of publications. So it does appear to be an exponential. All right, so a linear regression model for this data is calculated. The residual plot is shown. Is a linear model a good fit? So if you try to fit a line, notice that there's that curved pattern, right, that we see in the residual, so it cannot be very good. So no. Since there is a curved pattern in residual plot. Okay, it is suspected that the data follows more of an exponential pattern. Suppose we transform the data so that the response variable is the log of the annual number of publications. Predict what you think the scatter plot would look like. Well, if it's an exponential pattern, then when we take the log of the y-axis, it's going to make it linear, okay, if it's exponential. Okay, so remember that if you have a power model and you take the log of y versus log of x, it's going to make it linear. If you have a exponential model and you graph log y versus x, then it's going to make it linear. Okay, so in this case, we're going to say the data will appear linear if it's an exponential model. Okay, so the equation of the linear regression line for the transformed data is log of annual number of publications, hat, equals all of this. Okay, so use this model to predict the annual number of scholarly publications on the topic of AI in 2019. All right, so X is 2019 minus 2010. So that's the number of years since 2010. That's 9 years. So we get the log of Y hat equals 5.2096 plus 0.0402X. Now we're going to plug a 9 into that to get our log of Y hat. All right, so 5.2096 plus 0.0402 times 9, so 5.5714. All right, and again, like we did before, we got to get rid of this by doing 10 raised to both sides. So that cancels that out. So about 372,735 publications. Okay, all right, there you go, that's that one. So now number 27, data for the global CO2 emissions from the aviation for the 2010 to 2019 is given. They give you a transformation here. Okay, so because the data follows an exponential pattern, the emissions data was adjusted using a log transformation. So this is your equation, log of Y hat equals log of global CO2. Okay, all right, so you got the log. Okay, so they did a transformation here. They had the Y and then they did a log of Y. The computer output for a linear regression model is given for log of global CO2 emissions. Okay, so they basically did log of Y right there. Okay, given the equation, give the equation of the least squares regression line, define any variables used. Okay, so I'm going to say log of Y hat equals, now this is A, this is B. Okay, so you got 2.83 plus 0.021. Now, X is just going to be log of Y versus X. Okay, so you log of Y versus X. Okay, so we got just X here. All right. So where Y hat equals predicted global CO2 emission from aviation, and X equals number of years since 2010. Okay, so an exponential regression model was calculated. So they gave us that, where X is the number of years since 2010 and Y is the global CO2 emissions from aviation. Calculate log of 676.3153 and log of 1.05. Okay, so all we got to do is just calculate that. So we just do that on the calculator. You get 2.83015. Do this on the calculator. 0.0212. That's it. They just wanted to calculate that. That way you can kind of compare them. So notice that you compare this to that, and you compare this to that. That's the idea. So how are they related? Well, they're related because the constant term A is log of 677.3153, and slope term B is the log of 1.05. Okay. All right. So number 28, the technology company Apple spends money each year on the research and development of its products. Okay. Number of years since 2009, and the total amount of research on R&D in millions of dollars. Based on the scatter plot, do you think a linear regression model is appropriate? All right, so do you think a linear regression model is appropriate? Well, definitely not linear because it appears to be curved, right? So no. Since there appears to be a curved pattern. All right, so describe the relationship between the number of years. So basically describing it. So there is a strong positive nonlinear relationship between years since 2009 and total spent on R&D, research and development. In millions of dollars by Apple. Okay, that's it. I just wanted you to describe that. No unusual features, right? So I'm going to put here no unusual features. All right, so number 29, the heights and weights of a random sample of 22 individuals are shown. Okay. All right, and they're asking, is a linear model appropriate for these data? Well, the scatter plot appears to show a linear trend, and the residual plot appears to be random. Okay, so that's good. All right, so is a linear model appropriate? So now we'll say yes. So yes, the scatter plot appears to show a linear pattern, and the residual plot appears randomly scattered. Okay, so appears randomly scattered. All right, and it says it gives you the R squared value, but I don't really see the R squared value. I don't see that here. Hold on, let me see. Should they be giving you an R squared value? Hold on. Yeah, they should have given you an R squared value. So let me write that here. So the R squared value they got was 0.795 in this example, but they just didn't show you. So we could say the R squared value is pretty high as well. Okay. All right, so number 30, it says students are often given a standardized math test beginning of school year. Okay, so this is the end of year score versus the beginning of year score. And this is based on the scatter plot. Could a linear model fit the data? Well, I mean, it's a little bit tough to tell, but there might be a curved relationship. I don't know. It's kind of hard to tell. It looks like it could potentially, but there's a little bit of a curve to the data like that. So it's hard to tell from that alone. But if you look at the residual plot here, then you can see there's a curved pattern, right? There's definitely a curved pattern. And so you would say no based off of that. So, so I'm going to say, so let me just answer A. There is a slight curved pattern, so it may not be appropriate. But again, it's very slight, and only you can really tell because of part B, right? So so here we can say no, definitely for part based on part B, right? Not has a curved pattern. Okay, so the least squares regression line is calculated in residual plot. Yeah, so definitely not going to work then in that case. It says two other possible models for the data are shown. Which model is the best fit for the data? Okay. Okay, so this is model 1, model 2. Okay, so this should be model 1, and I guess this is model 2. Okay, so let's look at it. We got, this looks to be some kind of model here. It looks like they did a squared model, like they did y squared here versus x. So that's interesting. But look at that curved pattern. So it doesn't look very good, so it doesn't look good. However, it looks like they did log of the end of year score. So they did the log of y and the beginning of your score, but look, it's still curved. So which one's going to be better? Well, because they both appear curved, I would look at the R squared value. So here R squared is 0.987, here R squared is 0.99. So I would definitely, so I would say model 1 is a little better because it looks closer to linear. When I do that, and R squared is larger. Okay, so that's what I would say. I would say model 1 scatter plot appears more linear. And there is a very strong R squared value. Okay. So the next one, 31, the Cantril ladder is 0 to 10 score, a scale used to rate life satisfaction. So you got a Cantril ladder and the country's gross domestic product. Okay. And they will say, okay, which model is the best? Each model's computer output. Okay, so you got model A, model B, model C. Which one's better? So if you look at the residual plots, this one appears to have a slight pattern there. This one appears to kind of look like it goes like a pattern like that, where it's getting smaller. This one definitely looks more random. Like it definitely looks more scattered. So it looks more random. I'm going to say the most random compared to the other one. And it has a larger R squared. So I would say model B, the most random scatter, and the R squared value is the largest. Okay, so model B, most random scatter and residual plot with largest R squared. Determine the equation of your chosen model. Be sure to define any variables used. Okay, so they're saying that they did the ladder score, which is versus the log of the GDP per capita. Okay. Remember, GDP per capita is Y, and Cantril ladder score is X. Okay, so they did the Cantril ladder score, which is X, and then the GDP per capita is, okay, so this is log of y, and this is x, okay? So in that case, this is my a, this is my b. So let me just write the equation here. So we got log of y hat equals a plus bx. I'm using x because of the Cantril ladder score. The Cantril ladder score is x. Now here, if I were to use this model, I would be using log x, okay? So you just gotta be careful with that. So y hat is the predicted GDP per capita, and x is equal to Cantril ladder score. Okay, so that's B, and then use your chosen model to predict for a country with an average Cantril ladder score of 7.2. So log of y hat equals 2.163 plus 0.348. Now we're going to plug in 7.2 into that. Log of y hat equals, so we got 2.163 plus 0.348, then 7.2, so 4.6686. And then we're going to do 10 raised to both sides power. So that's $46,622.98. It's around there. Okay. On part D, the country with an average Cantril ladder score of 7.2 has a GDP per capita of that. So this is the Y. Using the prediction, calculate and interpret the residual. So residual equals Y minus Y hat. And then use what we got earlier to subtract those. $2,055.70 per capita. Okay, so that means now to interpret it, the actual GDP per capita is $2,055.70 more because it's positive, right? More than the amount predicted. By the model for a country with score of 7.2. All right, guys, that's going to do it for the video. Hope you found this useful and informative. And as usual, I'll see you in the next one.